begin my classes with questions. Are there any questions? Not a single one. Good.
I have a question. But I don't want to spend too long on it to get
I
you.
can't see you. Is that Dave?
Yes.
No.
So last time you were emphasizing that entropy isn't a property of a system. It's a property of a probability distribution.
At least as people like Shannon and Boltzmann.
That's for sure. Well, okay. So then somebody said.
Quantum mechanics a little more tricky.
Well, so somebody said about Boltzmann, gee, I don't think that's what Boltzmann had in mind. And you said, yeah, I'm not so sure of the history, but I don't think it was supposed to be just a historical point. That is, Boltzmann was trying to explain the second law of thermodynamics. Boltzmann was trying to discover the microscopic underpinnings of the second law of thermodynamics. Second law of thermodynamics is presumably something true of physical systems. Pieces of ice tend to melt, temperatures tend to equilibrate,
Not if you wait long enough.
so on and so forth.
Probably.
Yeah, probably.
Probably.
No, but it's a statement about an individual physical system that if it's a piece of ice in a warm room, it will probably melt. Okay? And what we mean by it will probably melt is that its thermodynamic entropy will probably rise.
Right.
So on some level, if that's what Boltzmann was trying to explain, and if that's what we're trying to explain in general in statistical mechanics, entropy is damn well better be a property of physical systems.
Yeah, I would agree with you.
Oh, good.
I would say in practice that's certainly true, but ultimately it is traceable to the mathematics of it, the properties of probability distributions, and how probability distributions evolve, how you coarse grain them when your eyeballs get a little bit fuzzy, and so forth. But I guess I really don't want to go there. But the one thing I'm going to say about your question is a little story about Dirac, which everybody knows. Dirac during the seminar was, somebody raised their hand and said, Professor Dirac, I have a question. Oh, what's your question? Well, I didn't understand that equation on the blackboard. And Professor Dirac waited and waited and waited and waited. And then the person said, won't you answer my question? Professor Dirac said, that wasn't the question. I would say the same. So, excuse me, I'm sorry. Are there any genuine questions? Yes?
Do you think that the laws of physics, whatever they end up being, have to obey unitary evolution and have to have information conservation?
I do believe so. Could I be wrong? Well, surprises happen. Look. Let me just philosophize for a moment, but I don't mean philosophize in the technical sense. Physicists are by nature very arrogant. You would have to be arrogant to say to yourself, I'm going to understand nature and I'm going to beat this thing called curiosity and lack of knowledge and so forth. It is an arrogant thing to try to do. And so the natural reaction when somebody asks you a question is to say, yes, that's exactly what I believe because it happens to be what I believe today. And today I'm right. Don't worry about what I thought last week. And physicists are arrogant. They're also among very good physicists a sense of humility. And the sense of humility, particularly as you get older, comes from having seen too many surprises. Having seen things change into unexpected directions, having seen things that you're absolutely certain were nonsense suddenly go off and be the right thing. You see that once, you see it twice, you see it 3 times, and it's humbling, shall we say. So I forgot what the question was, but whatever it was, let me take the both arrogant and humble view. Yes, I strongly believe that physics is unitary and information conserving, and I also strongly believe that there will be surprises that I can't predict. And what else can I that's what I have to say. Right? One more philosophically oriented thing. Earlier you heard about this idea of eternal inflation. It probably sounds to many of you like a degree of almost gratuitous speculation, too far removed from anything we can be certain of, and more than that, perhaps just a hobby horse of a couple of physicists with curious ideas. That's not the way this is working. The people who do this kind of work and who really originated these ideas were driven to them. They were driven to them by the logic. Now, it doesn't mean they're right. Again, surprises come in certain directions. But the logic that goes into things like eternal inflation, things like string theory, things like what I'm going to tell you today, sometimes feels very inevitable, and sometimes feels, despite your own prejudices and despite your own sometimes better judgment, you find yourself being driven in a certain direction. And you can't help but go there. That I think is the nature of much of the things that sometimes outsiders see as very speculative and almost gratuitous speculation. I don't think they are. I think the people who founded this subject of inflation, eternal inflation, and so forth, were not being speculative. They were reacting to circumstances and questions which just arose and led them inevitably to this view of things. Now, I think the same is true of what I'm going to say today. We're going to be talking about black holes. We're going to be talking about entanglement and the relationship between entanglement, but not just black holes, but if we get there, the relationship between entanglement and space and time. These are new ideas. They're different types of speculation. They're mostly built on mathematics rather than observation, but they are speculative, and they could wind up being wrong. So, but nevertheless, a large fraction of the theoretical physics community who think about these things have been driven to the same viewpoints. Okay, so we were discussing entanglement. Entanglement, in some sense, is the primary fact of quantum mechanics. It's the fact of quantum mechanics which makes it so strange, and it's the fact of quantum mechanics which gives it great power. I'll just remind you, just a buzzword for what entanglement means. When systems are unentangled, two systems which are unentangled and which have a state which is called a product state, you're in a situation where you know everything about the two individual systems that can be known. There are limits to what you can know in quantum mechanics. But in a product state, you know everything about the two systems, as much as can be known, but typically there's no correlation between them, so measuring something about one of them tells you nothing about the other one. The opposite extreme are these very entangled non-product states, called maximally entangled states, and maximally entangled states have exactly the opposite property. You can know everything that can be known about the composite system of two pieces, two things make up a composite system. You can know everything that can be known and still know nothing whatever about the two subsystems individually. What you do know is about correlation between them. You do know if you measure X in one of them, then you will definitely get X in the other one, or minus X in the other one, depending on the situation. And in fact, maximal entanglement is so pervasive that way that you can say in one of the systems, there is always something that you can measure which will tell you exactly what you would have gotten or will get if you measure something else in the other system. So that's the trade-off between knowing the individual systems separately, unentangled product states, and knowing the joint relationships between things in a highly entangled state. All right, now entanglement also has a lot to do with thermodynamics, and I just want to spell that out quickly because we're going to be moving on to black holes. And one of the things we're going to be thinking about and talking about is the thermodynamics of black holes. So let's go back to Alice and Bob's two systems, or a big system which has been divided into two parts called A and B. Let me just remind you of the basic formula for a density matrix. If you have a wave function, which is a function of the degrees of freedom, a complete set of commuting variables for A and for B, that's what we call psi AB. And if we're only interested in making measurements, or we only have access for one reason or another to the system A, system B may be far away, or maybe it's someplace safe, or maybe it's behind a black hole, we can only make measurements on A, then the thing that codifies all of the information about A is called the density matrix, and I'm just going to write the formula for it. You take psi star of A prime B times psi of A and B, and you sum it over B. Notice we're summing out everything having to do with B. It's called integrating out the degrees of freedom of B, and you have an object which is a matrix, A prime and A. Doesn't depend on B at all, depends only on A prime and A. It's a matrix, it's an operator in the Hilbert space of the system A, and it contains all of the statistical information of anything that you can measure about A. I'll just remind you, if you want to know the expectation value of something in A, you multiply it by rho and take the trace. Okay, so that's the idea of entanglement and its relation to density matrices. And finally, well, okay, that's enough of that for now. Let's come back to Alice and Bob's subsystem, and let's suppose we know one piece of information about the AB system. We know its average energy. We know the expectation value of its average energy and no more. Well, somebody created the AB system in some state. It's in some state, and depending on the state, the density, the state of a combined system, the density matrix of A may have a certain form. But there's a very interesting theorem that says that if the systems A and B are big enough, then for almost all states that you can write down, or not write down, it's not a question of writing them down, for almost all states of the AB system, the density matrix of the subsystem A, assuming that A is less than half of the whole thing, or maybe equal to half of the whole thing, the density matrix of A will have a specific form. And the specific form is the thermal density matrix. The Boltzmann, has everybody learned the Boltzmann distribution? I can't tell. Yeah. Okay, everybody else, quantum Boltzmann distribution?
Well, that sounds fairly answer both. Huh?
No, it's nothing to do with it. No. The density matrix associated with a Boltzmann, with a thermal system in quantum mechanics, the density matrix is an operator. Now it's an operator in the A subsystem, and it always has the form e to the minus beta times the Hamiltonian of the system of A. System of A by itself. In other words, if you have a big system and you agree not to look at half of it, and it's in a generic state, and the generic state, not especially chosen, but just randomly chosen from some library of states, then the density matrix of the A system will be of this form, e to the minus beta HA. Now that's an abstract thing, but let me comment on it more. Incidentally, there's a normalization factor to make its trace equal to 1. It's called the partition function in the denominator. It's not going to play any role in what we say. This is the form of this, the density matrix. And it's a phenomenon that does have to do with entanglement. If we take the AB system in some definite pure state, and we look at only part of it, typically what we'll find is that the part of it is described by a thermal density matrix. In other words, it looks like it's in thermal equilibrium. Now, every density matrix is diagonal in some basis, and a density matrix which depends only on the Hamiltonian is diagonal in the energy basis. In the energy basis, the density matrix is a matrix, and its entries are the eigenvalues of the density matrix, a set of probabilities. They're basically the probabilities of getting different values of the energy. And what are they? They're e to the minus beta E1, e to the minus beta E2, with zeros all off the diagonal, and simply tell you what the probabilities are for measuring different energies for Alice's subsystem. The eigenvectors of the density matrix are the energy eigenvectors of A. And that's the very, very typical thing which happens when you have a large system and look at a subsystem. This is the reason that when we have a large subsystem, when we have a large system, and look at a part of it, it looks like it's in thermal equilibrium, typically, generally. As I said, it is a consequence in this language of the entanglement between A and B. Remember, when you have product states, the eigenvalues of the density matrix are just 1, 0, 0, 0. For a highly entangled state, another statement here is that the average typical state of a two-part system like this is highly entangled. Entanglement is not an exception. Entanglement is the rule, and here's the way it works. Okay, what is beta? Anybody know what beta is?
1 over KT.
Forget K. We forgot. That's beta is 1 over the temperature. What is it that determines the temperature? The thing that determines the temperature is the average energy of the combined system. If you know the average energy of the combined system, that will tell you what the temperature is. All right, so that's one last thing. The entropy, the entanglement entropy between the two systems here is given by, let's write it, S entanglement is equal to minus the summation of the probabilities, these are the probabilities here, times logarithm of the probabilities. This is a definition of entropy that has to do with entanglement between two entangled systems and the density matrix of one of them. In fact, it's exactly the same as the thermodynamic entropy for highly entangled systems like this. So, one can think of thermodynamics as arising out of the properties of highly entangled systems. This is a theme that's gaining traction in the statistical mechanics world, the quantum statistical mechanics world. In any case, I will need it, so here it is. One more piece of language. I'm stating some pieces of language now. A and B, the combined system, assume it's in a pure state. A pure state means a very definite quantum state. The A subsystem itself is not in a pure state because the systems are entangled. Because they're entangled, the A system is in what we call a mixed state. One says in this context that B is the system which purifies A. What it means is if you have a subsystem A, and it's described by a certain density matrix, and that density matrix has an entropy, then you can imagine that it is part of a bigger system such that the combined system is in a pure state, a particular definite quantum state. And as I said, one says that B purifies A, which is just a statement that A and B together form a system which has a definite quantum state. Okay, that's language. What does this have to do with gravity? What does it have to do with gravity? So now we want to move on to gravity. According to Einstein, gravity is the same as acceleration. You know what I mean by that. They want the equivalence principle. That everything, you can learn about anything having to do with a gravitational field, an ordinary gravitational field. You know, somebody standing on the surface of the Earth. You can learn everything you want to know about the properties of physics to this person here by putting them in an elevator, accelerating the elevator, and studying the properties of what the world is like for that person in the accelerated elevator. So acceleration and gravity are the same. That's the equivalence principle. Let's try to quantify that a little better. An accelerated coordinate frame is simply a coordinate transformation of an unaccelerated coordinate system. For example, let Z be the vertical axis here. If I choose Z is equal to G over 2 t squared, where t is time and z is vertical height, you would say that, that this is an accelerated point, vertically accelerated. And if you were to write a coordinate transformation, z is equal to gt squared g prime squared. You would say that z prime is an accelerated reference frame. And you might draw the trajectories of the accelerated coordinate frame, t, z, they're parabolas. Each person in an accelerated coordinate system moves along a parabola. I've made the independent variable vertical, so if you want to see the parabola in the usual way, just turn your head on the side. Each person moves with an increasing velocity. First person, second person, and so forth. And the distance between them stays the same. Okay, now, that's an accelerated coordinate system. You can think of each observer in that system as being one of these lines. But clearly this does not work in special relativity. It doesn't work in special relativity because first of all, you're going to run into an immediate problem that if you wait long enough, these people will be moving faster than the speed of light. That's not good. Okay, we don't want that. But it's also true that because of length contractions, meter stick contractions, and so forth, if you were to actually have these people move along this parabolic trajectory, the distance between them, as measured by them, would not remain constant. This is not a good notion of an accelerated coordinate system in the special theory of relativity. So let's come to the notion of an accelerated coordinate system. Here I'm going to rely on a certain amount of sophistication about special relativity, not a lot. The main mathematical thing I'm going to assume you know is what a hyperbolic cosine and a hyperbolic sine are. If you don't, well, by a process of osmosis, you might figure it out. Everybody know what hyperbolic sine and cosine are? Mm-hmm. Kosh and sinh? Yep. Good, okay. Then we're cooking. Okay, so we begin by drawing space-time as Einstein, actually as Minkowski would have drawn it. I won't explain what this is, light cone and so forth. We have a vertical axis called t, we have a horizontal axis that I'll call z. And instead of drawing parabolas to describe a uniformly, I want to get rid of these to get in my way for a moment, but for z and t, each observer, let's say on this side of the diagram here, the observer is moving this way, he's coming in, slowing down, and going back out with uniform acceleration. Such a particle, observer, whatever it is, moves on a hyperbola. Not a parabola, but a hyperbola in special relativity. And the hyperbola is asymptotic to the light cone so that it never exceeds the velocity of light. Okay, so I think this probably is fairly familiar. Now you make a whole bunch of observers. Here's z at time t equals 0. Let's put the first one at z equals 1, the second one at z equals 2, the third one at z equals 3. And now let's propagate them forward in time on hyperbolas. All these hyperbolas asymptote to the same light cone out here. That's the notion of an accelerated coordinate system. The accelerated coordinate system is a collection of observers, and if you work it out, you'll discover that in their own frame, as they move, they maintain the same distance between them. In their own frame, one following the next, a line of them, they will move off, accelerate, and they will discover that they maintain the same spacing in their own reference frame at any given instant. So this is the closest you can get to what you would call a uniformly accelerated reference frame. The only thing that's odd about it is that the acceleration of the different observers is different. The acceleration of the ones out here is weak. The fellow in here, very close to the origin here, has a huge acceleration. That acceleration is constant with time. Each one sees a time-independent acceleration, but the sequence of them, the last fellow at the end here, sees a much larger acceleration. The first one, but you know, this, if you think about it a moment, that's not all that odd. Think about us on the surface of the Earth and imagine a stack of us, a very high building. In a very high building, believe it or not, the building has to be pretty high. But if the building is high enough, the person at the bottom of the floor, on the bottom floor, feels a larger acceleration than the person on the top floor. Isn't that true? Because the person on the top floor may be 10,000 miles away from the Earth, and the gravity on their feet is less. So it's not that odd that gravity, or that the equivalence principle, when we take into account everything that we have to take into account, involves frames of reference where observers, each one sees a uniform acceleration, but the different ones, one behind the other or one under the other, see different acceleration. Okay, so that's the notion. Now let's be quantitative about it. The coordinate which labels which one of these trajectories we're on, I will call rho. Rho has nothing to do with the density matrix now. I'm calling it rho. Rho is for R. The only reason I call it R is because R is already preempted by something else in black hole physics, namely the Schwarzschild coordinate. I'm just going to think of it as proper distance of the observer from the origin over here. Rho is constant along each one of these hyperbolas, constant proper distance from the origin, and it's one of the coordinates, and it's one of the various coordinates of space, rho. There's another coordinate, and the other coordinate goes like this. It's usually called omega. It's a hyperbolic angle. It's an angle variable along a hyperbola, but it's not an ordinary angle. It's a thing which goes into a cosh and a sinh, not into a sine and a cosine. It's not a periodic variable. Let's just compare that. Let's compare this with something else. Let's compare this with polar coordinates about an origin. Polar coordinates about an origin also have a radial coordinate, you could call it rho, and an angular coordinate. But the angular coordinate is really an angle. Here the angular coordinate is first of all a time-like coordinate. It points off in a time-like direction. It's not periodic. It goes from minus infinity down to the bottom of the blackboard, plus infinity at the top. But this is the time variable. This is the appropriate time variable for a uniform accelerated observer, omega, and distance from an origin over here is called rho. So the observer who is at a constant rho here, who experiences a constant acceleration, we can call a uniformly accelerated observer, and this time variable that takes off his time to his clock, his proper time, is just this angular variable omega. Well, Einstein said that gravity and acceleration are the same thing, so perhaps we should say, maybe if we understood physics in this accelerated coordinate system, perhaps we would understand a little more about gravity. And in particular, what I want to do is talk about quantum physics in this accelerated reference frame. Because maybe it'll give us a clue about how to think about quantum physics when we think about gravity. Okay, so that's our setup here. Do a little bit more of this. Let's write down, there's a t-axis here and a z-axis here. Those are the original coordinates, and now we've superimposed the coordinates of the uniformly accelerated observer, and I'm going to tell you the relationship between them. Z, the horizontal axis, horizontal position, is equal to rho times the hyperbolic cosine of omega, and t is equal to rho times the hyperbolic sine of omega. This look at all familiar? I can't tell if it looks familiar or not, but let me just compare it with something. If you really had ordinary angles and radial coordinates, so that this distance would be called rho, and this would be called angle theta. Let's call this one z. And let's call the vertical axis here t, even though it's just an ordinary vertical axis on the blackboard. What's the relation between z and t and theta and rho? The answer is z is rho times cosine of theta, sort of like this, and t is z times sine of theta. All you're doing going from ordinary Euclidean space to Minkowski space is substitute sines and coshs and sinh for sines and cosines. There's another way to describe it, and that's to say that omega and theta are related by a factor of square root of -1, or I, but don't worry about that. That's a technical subtlety that we don't need to know about. Okay, so this is the rho and omega are the coordinates that a uniformly accelerated observer would use. Now, nobody's asked me the question, but let me ask myself the question. These coordinates, as I've drawn them, only cover a piece of Minkowski space. Oh, let me add more. This is only 2 dimensions, z and time. What happened to the other dimensions, x and y? We can imagine x and y as 2 other orthogonal axes coming out of the blackboard. I can only draw one. I can't even draw one more, but I can put my arm here and make one more. But there are 2 more, x and y. And as far as x and y goes, they are just x and y. They don't change. The coordinates that are uniformly accelerated, we're talking about now, uniformly accelerated coordinate system, moving along with acceleration. The coordinates in the perpendicular direction to the acceleration are just the same coordinates that an observer at rest would use. So we'll just call those x and y. I won't bother. We'll just call this. Good. Any questions? Yeah. What happened to the other half, this wedge over here? We're not describing it by these coordinates. These coordinates are only suitable for studying a quarter of this geometry. In particular, they don't extend nicely. Omega goes from -infinity all the way up to +infinity without ever getting into this region or this region. So we're only discussing part of the space-time. It seems a little bit peculiar, and it is a little bit peculiar, but nevertheless, let me focus on everything that happens inside this wedge over here. In fact, it's everything that can ever be seen by one of these uniformly accelerated coordinate systems. Well, I take that back. I'm going to modify that in a moment. But in particular, imagine an event that takes place over here, or over here, or over here. None of these observers can ever see that event. Let's take one of these observers, no matter how late it gets, looks back along his own light cone and never sees light coming from here, here, or here. Impossible for a uniformly accelerated observer to see behind this light cone. It's called a horizon. This light cone here is the horizon, the event horizon for an accelerated reference frame. So already we found something interesting. We found that the equivalence principle is suggesting that whenever there's a gravitational field that extends far enough to the left, it will eventually reach a horizon. Unless something intervenes first. Unless something intervenes first. This is the most primitive version and simplest version of an event horizon. Now, of course, this accelerated observer could decide to stop accelerating. What's making him accelerate? He might be being pulled by a rope, or he might have jets to accelerate him. He could shut off his jets. He could cut the rope that's connecting him and pulling on him. And if he does, of course, he will just fall behind the horizon. He will fall behind this light cone, and then can see the things which are behind the horizon. But as long as that observer stays along these uniformly accelerated trajectories, or stays out of the region behind the horizon here, he cannot detect anything behind the horizon here. So from his point of view, this region over here is unphysical and, not unphysical, but just not important for anything. You never get a message from there. What about things in the region over here? Same thing. No signal can ever be gotten from this. This is usually called quadrant 1, quadrant 2, quadrant 3, quadrant 4. No signal can get from quadrant 3 into the region where our observers are. But what about region 4 over here? Region 4, yes. Things can be seen in here. So you might think that a description of this region over here is not really self-contained. You don't have to know anything about here, because you can't get a signal from here. You don't have to know anything from here, you can't get a signal from here. But what about things from here? And the way people think about this is the following. They say, this line down here, from the point of view of the uniformly accelerated observer, is in the remote past. It corresponds to omega equals minus infinity. Time, according to this observer's clocks, which are in the remote past. The observers in here can choose to use a language where they say that things that come in from region 4 over here are simply things that come in at time t equals minus infinity. In other words, they're initial conditions. They're part of the initial conditions of the world, of the isolated world that just consists of this quadrant, quadrant number 1. Quadrant number 1 has a name. I'll tell you what the name is. It's called Rindler space. Quadrant number 1 is Rindler space. And it's interesting because it potentially has a closed description that doesn't depend on any of the other things here. A closed description in terms of its own dynamics and in terms of its own, except that it needs an initial condition to tell us what happened at t equals minus infinity. What are we learning? We're learning something. We're learning something about how acceleration works. Whether it has anything to do with gravity is another question, but of course it does. It doesn't do a lot with gravity, it has to do with black holes. Okay, so let's think about these observers who stay in quadrant number 1. There are degrees of freedom in quadrant number 1. They might be quantum fields. They might be electromagnetic fields, quantum or classical. They might be electromagnetic fields. They might be whatever, particles, whatever's in here. And how does a good quantum physicist or even a classical physicist describe the evolution of a state? Here's an instant of time in the accelerated coordinate system. Here's a later instant of time. This could be omega equals 0. This could be omega equals 1. How does a quantum physicist or even a classical physicist describe how things evolve from one time slice to another? Well, the answer is, of course, equations of motion. But in particular, the use of a Hamiltonian. A Hamiltonian is a thing which takes you from one time slice to another, and it takes you. We've learned some quantum mechanics, so I'll write an equation. The usual equation is that if you want to know how the state vector changes with time, its time derivative is given by acting on the state vector with the Hamiltonian. So, if we want to know how a state vector in this Rindler space changes with time, the answer is I, there's always an I in quantum mechanics, a certain Hamiltonian. And this is the Hamiltonian for propagating from one Rindler time to the next. It takes you, it's kind of an angular shift time side. And it's called the Rindler Hamiltonian because it's the appropriate Hamiltonian for the uniformly accelerated observer. Okay, I'm going fast and I'm prepared to take a question or two about it if I'm slowing you, and so I'll slow down.
Is that a hyperbolic parabola? Can we go around and think about the rest of it, or that?
No.
Figure of revolution?
No, it's not a figure of revolution. It's a figure, it's a, X and Y come out of the blackboard, so it's a hyperbolic cylinder. If you went back to here, and you introduce the other coordinate, let's say one other coordinate, yeah, right, I know you know. This would be a cylindrical coordinate system, not a spherically symmetric coordinate system, cylindrical. Okay, so it's the Euclidean version of it would be an operation which takes you from one angular slice to the next angular slice. Tells you if you know something on this angular slice, it tells you what's happening on a neighboring angular slice. In Minkowski space or Rindler space, it's telling you what happens from one Rindler time, that's an omega, to the next Rindler time. And it's just the ordinary Schrodinger equation, except in this set of coordinates. Okay, what do we expect physics to be like for this system of Rindler observers? They have their own Hamiltonian, they have their own coordinates, there's even a metric. Let me write down the metric. Let me write down the metric. The metric is just the metric which is inherited from the original Minkowski space. ds squared, which of course is equal to dz squared plus the x squared plus the y squared minus dt squared, the usual Minkowski metric. But if you write it in terms of rho and omega and x and y, it just becomes rho squared d omega squared with a minus sign. Time always comes with a minus sign. Minus rho squared d omega squared plus d rho squared plus dx squared and dy squared. I won't bother writing y squared. Y is the fourth coordinate plus dy squared. Just x squared stands for both x and y. This might also have a familiar ring to it. Maybe yes, maybe no. But I think you might not be too surprised if I wrote down the metric of the ordinary plane in the form rho squared d theta squared plus d rho squared, and then an additional coordinate sticking out of the blackboard. This look familiar? Shout it out, yes.
Yeah.
Okay. If you replace theta by I omega, it just becomes this. Rho squared d omega squared with a minus sign, plus d rho squared, and then the other coordinates which are perpendicular. And this is the metric of Rindler space. Now, it has a curious feature. This is a time component. Think of omega as a kind of time in the accelerated coordinate system. Notice what it does at rho equals 0. It goes to 0. Time slows down in some funny sense at rho equals 0. It's really just an artifact of the coordinates. There's nothing crazy going on here. But still, for the accelerated reference frame over here, the metric contains this rho squared in front here, which says that the proper time along these trajectories as a function of omega depends on which trajectory you're at. Time flows differently on these different trajectories as a function of omega. Proper time does. This, of course, is the phenomena that happens at the horizon of a black hole, where the time component of the metric also is 0 at the horizon of the black hole. So this starts to suggest, for several different viewpoints, that rho equals 0. Rho equals 0 is very close, or actually right at these light cones. That is the analog, or perhaps the prototype, of a horizon of a black hole. And that's exactly what it is. That's what we'll find out. That this is the horizon of the black hole, looked at from very close to the black hole. Looked at from very close to the black hole. This is what we're seeing. Seeing time slowed down, proper time slowed down. And okay, now let's the observers on this side, let's call them Alice. We could also imagine a family of observers on the left side. They could also be there. They won't have much to say to Alice because they can't get a signal across to Alice. There's no way a signal can go from here to here. Let's call them Bobs. Alice is on the right side, Bob's on the left side. And from the point of view of Minkowski space, from the point of view of usual relativity, where we might think about initial conditions at t equals 0 on the whole infinity of space here, Alice and Bob now have access, each of them, to only half the world. Alice, and any one of these Alices, only has experiences from this half, can only detect things from the initial conditions on this half. The other half is irrelevant. Likewise, Bob's on this side never have anything to do with Alice's initial conditions. This is sounding quite a lot like, that's quite a lot, it is. Taking a system, which now consists of the entire space at time t equals 0, and dividing it into two portions, Alice's portion and Bob's portion, and asking, what is Alice's description of her part of the world if she never gets to look at Bob's portion? Well, the answer is going to be a density matrix. The answer is going to be a density matrix which is constructed from whatever we know about the state of the whole system by doing the process of integrating out Bob's degrees of freedom. In other words, exactly the process we use to eliminate Bob out of Alice's description. I erased it, but I should put it back. To construct a density matrix. Now, is it going to be able to, let's try to foresee some of the things we might discover. One of the things we might discover, I want to focus on in particular, it has to do with fluctuations in quantum fields. The natural description in special relativity is to describe everything by quantum fields. Quantum fields fluctuate. Like anything in quantum mechanics, they fluctuate. And I'm not going to go deeply, I'm not going to go even shallowly into the theory of quantum fluctuations, but I'm just going to give a pictorial description of them. The pictorial description is very close to Feynman diagrams. In fact, it is a kind of Feynman diagram description. I won't try to make it precise. It's just to draw some pictures. In a quantum vacuum, there's a continuous process of pair creation and annihilation. Particles are produced. This is vertical as time as usual. Particles are produced and annihilated. Particles are produced all over the place. The vacuum is full of these things. I'm going to take that as a model for what quantum field theory is like. Constant, repetitive, everywhere in space, creation and annihilation of pairs of particles. Now, of course, it's more complicated than that. Triplets of particles can be produced, particle pairs can be produced, they exchange other particles, but that's not important. Okay, let's come to Alice's side over here. Alice's vacuum, I wish I had some other color, no other coloring. Okay. Alice's vacuum over here has quantum fluctuations. I'm going to erase. Rid of all these coordinates, clean up Alice's vacuum. Alice's vacuum from time to time, not from time to time, very regularly, has microscopic fluctuations. Incidentally, these fluctuations are microscopic, typically, and they don't last very long. That's why we don't see them. They last a microscopic amount of time, they come and go, and they're called virtual. They're called virtual because they come and go, and they don't last long enough time to be able to see. Okay, here's a fluctuation, but there are also fluctuations that look like this. They're half on Bob's side and half on Alice's side. From the point of view of the non-accelerated reference frame, these and these are exactly the same. This is just a fluctuation that happens to take place in a position where one particle was on one side and the other particle was on the other side. What the question?
But interpreting that, what you just drew, it seems like it originates in quadrant 4.
It does originate.
So from the perspective of A and B, the origination is sort of looks like an initial condition?
It looks like it originated in the infinite remote past. Remember that here is the infinite remote past. Omega equals minus infinity. Here's omega equals plus infinity. So, from the point of view of Alice, all of this is in the very, very remote past.
But it's supposed to also be very transient. So, trying to understand that in.
You're asking the right question. Okay, so here we have a phenomenon from the point of view of the unaccelerated reference frame. It looks like a very rapid transient. Particles come and go. But let's look at it from the perspective of Alice using her own coordinates, which are these accelerated coordinates. This line over here and this line over here are rho equals 0. You can think of it as the floor, except it's a very funny kind of floor with an infinite acceleration. It's not really the floor, it's just, this one is a long time in the past, this one's a long time in the future. And what happens? A particle jumps out, starts out at rho equals 0, rho equals 0, it starts out at rho equals 0, and it jumps out to some much larger rho, and then it falls back in. From Alice's point of view, she looks back and she sees a particle in the very, very remote past jump out from the horizon, jump out from rho equals 0. Let's plot it over here. Let's plot it differently over here. Let's make a plot in which here's rho equals 0. I don't want to, better not introduce more coordinates, I'll just confuse you. What Alice sees is a particle that lasts forever. I think that's what you were getting at.
Yeah.
It seems to last forever, although for a very long time in the past, it was very close to the surface near rho equals 0. It jumps out and then falls back in and takes an asymptotically long time in her frame of reference. She never sees it actually fall quite in. No matter how late and how hard she looks, She always sees it in quadrant number 1, asymptotically falling toward the floor, if we want to call this the floor. And so what she sees is basically a very, very long time history in which this piece of chalk starts very close to the floor, jumps up, and falls back. That's called gravity. This is exactly the phenomenon of acceleration reproducing gravity. A particle which jumps out and falls back, except that this particle was a vacuum fluctuation. It wasn't something that somebody threw in from outside. It was a part of the vacuum. So what a Minkowski observer, an observer at rest, would call a vacuum fluctuation, Alice calls an energetic particle jumping up from the floor and then falling back down. But this doesn't just happen once. There are many such vacuum fluctuations, up and down the x-axis here, many of them. She continuously sees particles jumping out of the floor and falling back down. What could possibly, and these are fairly energetic particles, incidentally, they may or may not be energetic. What would you think if you saw, coming up out of the floor, continuous particles jumping up and falling back down? You might think there's some source of energy in the floor. You might even think the floor was hot, and what's happening is that it's ejecting particles because of the thermal energy. And the particles are just falling back down to the floor. That's what you might think. So Alice out here sees something which, under other circumstances, we would call vacuum fluctuations, but she sees them as a kind of thermal fluctuation, as a kind of thermal excitation, which is ejecting particles which then fall back down by the simple expedient of gravity. She might even come to the conclusion that the horizon at rho equals 0 here is hot. She might even come to the conclusion that the horizon is hot because every time she sticks her finger into that region, it gets bombarded with these particles. And these particles are not virtual particles from her point of view because they last forever. They're not a transient. They last from time minus infinity to time plus infinity. All right, that's...
How does she, these last from minus plus, and where's the time that she sees it in?
Well, she might see it over here. She stuck her finger over here. Particle, let's turn this on the side. Here's the floor, which means rho equals 0. Here's rho going this way, and a particle jumps up out and falls back down. And if she sticks her finger there, she'll intercept it. And she may get burned. She'll get burned. So that raises the question. This is just a picture, but it raises the question, what's the mathematical framework for Alice's description of nature if she wants to ignore Bob's side? And she will ignore Bob's side because she can't see. What's the mathematical description? The mathematical description begins with knowing the state vector, knowing the wave function of the vacuum. Let's throw it over here. The vacuum of Minkowski space. When I say Minkowski space, I mean both sides represented in the usual coordinates, in the usual Cartesian Minkowski coordinates. There's the right side that we call A for Alice, the left side that we call B for Bob, and nature provides us, or mathematics provides us, with a vacuum state. The vacuum state is the ground state of a quantum field theory, whatever quantum field theory happens to be. Wave function is a function of the degrees of freedom of Alice and Bob. It's a psi of A and B. What are the degrees of freedom that Bob and Alice see? The answer is quantum fields. quantum fields at each point of space, but we don't have to specify them. We don't have to specify what they are. Whatever Alice has access to, we'll call her degrees of freedom. Whatever Bob has access to, we'll call his degrees of freedom. And I'm now going to tell you a theorem about the ground states of quantum field theories. The theorem is a beautiful theorem. It's easy to visualize in a way. I'm not going to try to explain it or prove it. It's called the Feynman-Katz theorem. Katz is K-A-C, the mathematician Mark Katz. Feynman-Katz theorem. I don't have to spell Feynman, do I? No, I don't. All right. For mathematicians, they would laugh at me if I spelled Katz. Sounds like K-A-T-Z, right? Well, it's the same name, but it's K-A-C. Mark Katz. Feynman-Katz theorem boils down to the following prescription. If you want to calculate the ground state of a quantum system, and in this case it's a quantum field theory, what you do is you write a path integral. Now, you may or may not know about path integrals. You write a path integral that is constrained by saying the initial state, path integral over the upper half space here, you do it pretending that the time was a Euclidean time. Not a Minkowski time, but a Euclidean time. You pretend space-time has a Euclidean metric. You pretend that the angular variable, the time-like angular variable, is really an ordinary angle. And you construct a path integral. The path integral is e to the minus the integral of some Lagrangian. I'm not going to take you through any of the details. Path integral integrated over Alice and Bob's degrees of freedom, up here, the whole works. But the bottom line is that the way that you calculate the ground state is by fixing the initial conditions, Alice's coordinate, Bob's coordinate, and propagating upward using the path integral to infinity with Euclidean coordinates. Now, I absolutely appreciate that this is a bunch of gobbledygook. I'm going to show you what it boils down to, though. I'm going to show you what the answer is. One way of doing that path integral is not to divide the space vertically, but to divide it angularly and propagate from one angular surface to the next angular surface. I'm going to write down the answer now. I'm going to write down the answer for the wave function of the vacuum, the wave function of the vacuum as seen by the Minkowski observer. And it's very simple. You pretend that there's a system which is propagating over time from A to B, where you think of the angle as time. Think of an angle going from here to here, starting with a quantum state along Alice's line here, and propagating it from step to step to step to step until you get to Bob's side. And I'll write down the formula. You may recognize the formula. The wave function of the system, A and B. Here's what it is. You start with a state of Bob's half of the world. Sorry, Alice's half of the world. You propagate with e to the minus the Ringler Hamiltonian, the same Hamiltonian that we used to go from one Ringler time to the next, exactly the same Hamiltonian, times the amount of time that you propagate from here to here. Does everybody know the formula that to propagate something from one time to another, you use e to the odd ht? Yeah, okay, that formula is known. That's all I'm doing here, except instead of a time, I'm using the angle. Well, that gives us e to the minus the Ringler time times the total angle that you propagate from here to here. And that's pi. All right? So you start with the state A over here, which is Alice's description of the initial state, and you propagate until you get to B. Equals. It's a transition matrix element in a fake quantum mechanics problem, starting at A and propagating around till you get to B. Now you may ask me, what happened to the I that usually occurs in here? Well, it's just not there. It's not there because angles and hyperbolic angles are related by a factor of I. All of this is very technical. I've tried to just summarize it in a quick, simple formula. But I'm going to show you what it's good for. It's extremely powerful. Well, this is crazy. I mean, it's such a simple expression for knowing the whole wave function of a quantum field theory. It seems a little ridiculous that this is all I have to write down. But of course, keep in mind that doing the problem of propagating from A to B might itself be a monstrously complicated problem. We don't have to do it. Okay, next step is to carry out the construction of the density matrix. Of course, by now, you should realize that we're deeply into entanglement land. We're talking about the description of a highly entangled system, the two sides here, in a situation where Alice doesn't get to look at the other side. So, we have a highly entangled state between A and B, and we're trying to work out the density matrix of the inside. That's not hard to do. We just carry this out now. We start with A, e to the minus h pi. I won't bother writing the Windler sign for r, hr, just h. B. That's this term over here. And this term over here, that's b, e to the minus h pi, whoops, e to the minus h pi, a prime, b, b, e to the minus h pi a. And we sum over b. So all of the experts in quantum mechanics will immediately recognize that when you sum over b here, what do you do with that, sum over b?
Get one.
Just a unit operator. You just throw them away. And you write that this is h pi. This whole thing is just the matrix element between a prime and a of e to the minus 2 pi h Windler. 2 pi, because it's e to the minus h pi times h pi. Now this is a highly formal mathematical trick. Mathematical trick. Believe me, it has substance to it. It's correct. It tells you what the density matrix between A and A prime is. A and A prime have only to do with Alice's side. It tells you what the density matrix is in terms of the Windler Hamiltonian. In fact, what it says is that the density matrix itself as an operator is e to the minus 2 pi hr, h Windler. Okay. Now I want to go back to our thermodynamics, or to our earlier discussion of the Boltzmann density matrix. The Boltzmann density matrix was beta and rho equals e to the minus beta h. That was the density matrix that describes a system in thermal equilibrium. We've done a trick and a series of tricks, and what the series of tricks tells us is that Alice's description of nature on this side is described by a density. We might not know what the Windler Hamiltonian is. We might not even know what the fields that describe it are. But what we've learned is no matter what they are, the description of Alice's sign over here is thermal. It has the form of a thermal density matrix of exactly the type that you expect when you have a two-part system and you put it into a random state. Thermal density matrix. But what is the temperature? peculiar temperature.
1 over 2 pi.
1 over 2 pi. So we have a very odd situation now. Alice sees a world at a very definite temperature, and the temperature is 1 over 2 pi. I'm waiting for somebody to ask me whether it's centigrade or 1 over 2 pi. How much?
Well, you started 15 minutes late, so it's another 20
Want
minutes.
to go to 15 minutes? Is that okay?
Absolutely.
No, I can stop.
No,
Okay. Temperature 1 over 2 pi. Centigrade? Nah. In fact, 1 over 2 pi, what units is 1 over 2 pi? 1 over 2 pi is a dimensionless quantity. How do we manage to get for temperature a dimensionless quantity? Now, what is the natural units for temperature? The natural units are energy. We talked about that the Boltzmann constant is just a conversion factor. The natural units for temperature are energy. How can it be that we got a dimensionless answer for the temperature? Well, that goes back to our choice of time variable. Time and energy are conjugate to each other. There's an uncertainty principle, for example. Delta T, delta energy is equal to Planck's constant, and if we take Planck's constant to be 1, and this is just delta T, delta E equals 1. Whatever units we use for time, the units that we will wind up using for energy are simply the inverse units. Time times energy, if we set Planck's constant to 1, is just equal to 1. So units of time and units of inverse energy are the same. That would suggest that temperature should have units of an inverse time, and that's correct in these kind of units. Temperature has units of an inverse time, but our time unit, our time variable, this omega, that's a hyperbolic angle. A hyperbolic angle is like an ordinary angle. It has no dimensions. It's dimensionless. How did we wind up getting a time which didn't have units of time? Or length. Length and time have the same units in relativity. How did we manage to get a dimensionless temperature? And the answer is because we were using a dimensionless time, which gives us a dimensionless energy. Well, let's go back to the drawing. Here's omega. Omega is these angular slices here. But now let's imagine Alice, who is a certain distance away from the horizon, from the origin. How much proper time goes on between successive omega times? How much proper time is there when omega goes from 0 to 1, let's say? That's going to depend on how far away she is. Same as over here. Same as angles. How far do you go from one angle to the next angle? It depends on what your radial coordinate is. So in fact, if we were to look at the proper time along Alice's trajectory over here, the proper time along Alice's trajectory, let's call it tau, the proper time along Alice's trajectory is rho times omega. The bigger rho is, the more actual proper time elapses between these coordinate time sections here. Another way to say it is that rho is a conversion factor from dimensionless time to the proper time that Alice experiences along those trajectories. If there's a conversion factor for time, there's a conversion factor for energy, and the energy conversion factor is the inverse. That tells us that what Alice actually experiences is a proper temperature. In other words, a temperature she would actually detect with her real, honest thermometers that is not 1 over 2 pi, that doesn't mean anything, but there's an extra conversion factor of rho, and the temperature that her thermometers would record is 1 over 2 pi rho. That's the correct. If time transforms with a rho in the numerator, energies transform with a rho in the denominator. So the upshot of this is very interesting. It says that Alice experiences a world where her thermometers will record a temperature which gets bigger and bigger and bigger as rho gets smaller and smaller. If she's holding on to a thermometer or dangling, Alice might be way out here, for example, on a very weakly accelerated trajectory. She might be hanging down by a rope, a thermometer. She lowers that rope. Maybe it's better than a rope. Maybe it's an electrical cable so that she can read the temperature. She lowers it down, and the lower she lowers it down, the closer she lowers it to rho equals 0, she sees a temperature which goes like 1/2 pi rho. It gets very, very hot near the horizon, near the rho equals 0 horizon. So we see from this, we see some rather extraordinary things. We see that, first of all, Alice's description is not what you might have expected because she's entangled with Bob's side. Alice's description is not in terms of a standard quantum mechanical state vector, but in terms of a density matrix. Why? Because she's entangled with the other side. We work out the entanglement, and we find out that Alice's density matrix is in fact exactly the density matrix of a thermal system, but with a dimensionless temperature that's just 1/2 pi, that corresponds to a variable temperature as you move out, which gets lower and lower, higher and higher. How come the temperature varies from one place to another in this way?
Well, it has to do with the acceleration.
It has to do with the acceleration, but it's another way of another way to think about it. Redshift. Redshift. If you were to measure, if you had a hot object near the floor here, and it was producing black body radiation, you hold your thermometer down near the floor, and you see the radiation temperature. Now you take the thermometer up. The photons in that black body radiation redshift. They lose energy as they climb up out of from the floor. They lose energy, and because they lose energy, the effective temperature does vary as you go up and down. Temperature as measured by the energy of the photons that hit your detector. So if you had a hot floor and a long, long column, long enough and the gravity was strong enough, you would in fact suspend your thermometer and you would find that the temperature, the actual temperature measured by the thermometer varied in this way. So it's not that odd a phenomenon. What is odd is that Alice sees the temperature altogether. After all, there was nothing in Minkowski's space here that was hot. She sees heat because she's ignoring half the entangled state of the world, and therefore sees fluctuation that she can't account for because she just doesn't see the other side. All right, that's I think it's a good place to put. That's up to you.
I think you still have a punchline or two coming, don't you?
Oh, of course, but you can do it next time too.
I mean, you started late, so I think
Okay,
you can
fine.
take another.
I just don't want to wear out the others. Punchline, of course, is what does this have to do with black holes?
Exactly.
Sure, of course. All right, now, we haven't even written down the black hole metric yet. I think I'll save writing down the black hole metric for the next time, but tell you qualitatively what the connections are. If you have a black hole has a horizon. Now, I know I haven't defined that yet, but nevertheless we will. And the horizon is mathematically a surface which is analogous to the polar coordinate point over here. We'll come to it. The outside the horizon is like being in the exterior region on Alice's right-hand side here. Being inside the horizon is being behind the horizon over here. But just accept it for a moment. A black hole has a horizon. Now, the horizon is a sphere. Depending on the mass of the black hole, the radius of the horizon is twice the mass of the black hole, Newton's constant divided by c squared. And let's imagine it's big. Let's imagine that the horizon of the black hole is big. Alice on the outside cannot see what's inside. Her whole experience in life is what's on the outside of the horizon. And if she looks in a small region near some point on the horizon, the logic is the same as looking at a small region in the neighborhood of some place on the surface of the Earth. What do you see when you look on the surface of the Earth, in a neighborhood of a point on the surface of the Earth? You see flat space, a very flat Earth. You see a constant gravitational field, as long as you don't go too far away from the surface. And you see the coordinates of the surface being just Cartesian ordinary coordinates. A mathematician would say you're looking at the tangent plane to the surface of the Earth and replacing the surface of the Earth by its flat tangent plane. And as long as you don't move too far from the surface, the gravitational field will look absolutely uniform. And so you might expect that what someone on the outside here sees is analogous or similar to the uniformly accelerated coordinate system. And that's correct. We can work that out. But if we focus in on a small piece of horizon over here, there's inside the horizon, there's outside the horizon. The exterior part of the horizon looks exactly like window space, close to the horizon, in a small region here. It looks exactly like window space. The upshot is that somebody suspended above the horizon here with their thermometers will see a temperature which is also of exactly the same kind. Temperature equals 1 over 2 pi times the distance from the horizon. That's called the en route temperature. We haven't quite got to the Hawking temperature yet. The Hawking temperature arises because of a conversion factor between, which we'll work out next time, between this dimensionless variable here and time seen from far away from the black hole. An observer far from the black hole versus an observer very close to the black hole sees a redshift and sees clocks go at a different rate than clocks near the black hole. The relationship is that the time as seen from far away, an observer far from the horizon, divided by 4mg, mass of the black hole, g, is equal to omega. All right, what is this 4mg? It's a conversion factor. It's a conversion factor from dimensionless time to the time as recorded by an observer far away. The implication is that the observer far away will see a temperature which is 1 over 2 pi times the conversion factor between omega and t. And what does that give? It gives 1 over 2 pi times 4mg in the denominator. I'm leaving out for the moment speeds of light, Planck's constant. I'll put them back for you in a moment. And what it says is these particles which were discovered from the equivalence principle. By saying, let's forget gravity, let's just think about an accelerated coordinate system. We discover in this odd way that the accelerated coordinate system sees particles constantly jumping out of the horizon. We now take Einstein's advice and say gravity should do the same thing as the accelerated coordinate system does, namely particles jumping out of the horizon. But because of the redshift factor, the energy of the particles when they get far away will be much less than the energy of the particles when they're emitted nearby, and that's this conversion factor. So somebody far away will ascribe to the horizon of the black hole a temperature 1/8 pi times the mass of the black hole times the Newton constant. And this is not quite right. That's because I've set h bar and c equal to 1. I told you I would do that last time. I've done it. But let me put them back for you. There's an h bar in the numerator. That, first of all, tells you that this temperature is a quantum effect. Without quantum effects, without quantum mechanics, there would be none of these virtual fluctuations, which look like particles jumping out of the horizon. It's a quantum effect. And so the temperature contains an h bar. If h bar was 0, the temperature would be 0. There's also a c cubed, the speed of light cubed. This is the Hawking temperature. This is the famous Hawking temperature of a black hole, the Hawking. And I want to emphasize again where it came from. It came, first of all, from using the equivalence principle to say what we should be studying is accelerated coordinate frames, and then realizing that an accelerated coordinate frame only covers half the space. And so to study what's happening in your half, you have to get rid of the other half. That involves density matrices, and it involves studying half of an entangled system. So we see that entanglement is providing the underpinning for the thermodynamics of black holes. Next time we'll talk about how entanglement is connected with the structure of space and time itself. Here, this is just a statement that a black hole has a temperature. Okay, black hole has a temperature. We're going to find out that entanglement is much deeper, and that the whole ability to be able to say that Alice's half and Bob's half belong to the same space, that they're connected, that Alice's half and Bob's half are really joined together at the center into a single space-time here, is ultimately due to the entanglement between the left side and the right side. Entanglement is what holds space together. That's going to be the theme of the next lecture. We'll also talk about entropy. We haven't talked about entropy. We talked about temperature. We're going to work out the entropy of a black hole, discover that the entropy is proportional to the area of the horizon. We'll talk a little bit about the holographic principle, but then I want to move on to the sense in which entanglement is what holds space together, if you like. Okay, good. Let's. Yeah.
If we are basically Alice's system, and that implies that Bob's system has to be somewhere.
Behind the horizon of the black hole.
Right. Okay. So what can we learn?
And probably, at some point, I'm probably going to switch and put Alice behind the black hole. That's my own. What can we learn?
So what can we learn about Bob's system?
This is the question. The question is, what is it that encodes Bob's world? What is it that encodes, what is it that describes Bob's world from the point of view of Alice on the outside? Now, the answer is roughly the following. And whenever you have highly entangled systems, there is something that you can measure in one of them that tells you any given piece of information you want in the other. It's the entanglement between the two sides that provides the bridge between the outside and the inside of the black hole. Now, is it useful for prediction? Is it useful to be able to predict? I don't know if it's useful to be able to predict what Bob sees on the inside of the black hole. But the point to learn here is that the inside and outside of a black hole are connected and not just connected, but are related to each other by exactly this phenomenon of entanglement. Anything you want to know about what's happening to Bob on the inside, there's some measurement that you can do of some observable on the outside. Now, the question is, how do you confirm it? You can't ask Bob behind the horizon. Alice can try to jump in and find out what happens, and there's an interesting story there. So, but again, I'm going to emphasize this is a relatively new idea. It's an idea of the last 10 years. I think it does not predate the turn of the century, that the structure of space that holds it together, what keeps it from falling apart, is entanglement. And I'm going to show you some examples of how entanglement actually holds space together. Yes, ma'am.
So there's a third guy in your Riddler space example, and something I've always been confused about when I see this direct analogy between the technical computation we've done in Riddler space and the thing that's going on in the black hole, is that in Riddler space you forgot about Mr. Milne. So Alice and Bob aren't really happy.
Oh, Mr. Milne.
Yeah, Mr. Milne, meaning number 2, right?
Number 2.
Number 2. So in the Riddler calculation, well, I mean, Mr. Milne wouldn't see anything, right? So those are inertial observers. So they don't see anything funny going on.
Mr. Milne might just be somebody who falls through the horizon freely, for example.
Yeah. But
Who's Mr.
here's
Milne?
my point. Here's my question.
Mr. Milne is.
Well, here's my question. So why is it that this computation that I've done here, gives me the right answer? Technically, I understand what's going on. But nevertheless, I've neglected this stuff going on in that quadrant 2, that Milne patch, right? So one can imagine, well, the degrees of freedom of Alice might be entangled with the degrees of freedom of Milne.
They are.
They are, right?
They are.
They are.
They are, but the way to think about it, okay, who is Mr. Milne? Alice lives here, Bob lives here, Mr. Milne lives here. Now, Alice is entangled with Bob, which means that everything that you might want to know, or at least a lot of what you might want to know about Bob, there's some measurement that you can do on Alice's side here. What's also true is that at least half of what comes to Mr. Milne, and not just what comes to Mr. Milne, but what describes Mr. Milne's degrees of freedom over here, comes either from here or from here. Let's take the half which comes from the left side. Meaning to say, when you solve the equations of motion for fields in Mr. Milne's territory over here, they trace back to what happened in the past. And in particular, they trace back to about half coming from Bob's side and half coming from Alice's side. Let's concentrate on the stuff that comes from Bob's side over here. So Mr. Milne's fields over here are really equivalent to an evolution from fields from Bob's side. So if Bob is entangled with Alice, let's just represent entanglement by some new kind of symbol. Alice and Bob are entangled over here. That entanglement will be inherited as an entanglement between Alice and Mr. Milne. Just because every operator of Mr. Milne's over here really traces back to Bob or Alice. Does it?
Yeah, that helps. I see that. When we talk about black holes, we talk about a temperature, even though I don't imagine that there is on the other side of the wormhole. So, what I'm thinking is, I say this, in reality, I don't think about this other, there's no wormhole. Light collapses starting in a black hole. Now there's stuff going on inside the horizon and stuff going on the outside.
I think you should start to think about the wormhole.
Yeah, you're right.
That, the entanglement between Bob and Alice in the black hole, that sounds like you can send some information about Bob through the black hole to Alice.
No, entanglement does not allow you to send information. Okay. There's something that we should have talked about from the beginning. Entanglement is some kind of relationship between different systems, but it is not a relationship which allows you to communicate from one to the other. Let's start with the classical analog of entanglement. The classical analog of entanglement is just statistical correlation. All right, we start with Charlie. Charlie has behind his back an eraser and a piece of chalk. Alice and Bob come over to him, and without looking at what they get, and without, maybe even Charlie doesn't look very carefully, they all close their eyes. Charlie holds out his chalk and his eraser, and Alice takes one, and Bob takes the other. They put it in their box, and they don't know which one which they have. They fly apart. Alice goes off to Alpha Centauri, Bob goes off wherever he goes, and then at some later time, they are correlated. They're statistically correlated in the sense that if Alice looks at what she has and it's a piece of chalk, she knows instantly that Bob has the eraser. But that doesn't tell Bob anything. Bob doesn't know that information. Bob cannot learn about Alice's experiment until a time necessary for light to travel between Alice and Bob. So statistical correlation, and that statistical correlation came from the fact that they were at the same place in the past. They were in the same place in the past, they interacted with each other, something happened which correlated them, and then you took them apart. That does not allow the transfer of information from one side to the other. In no way does that allow Alice to signal Bob.
Well, not transfer, but you know something about Bob in there that if they're correlated.
You really shouldn't be surprised by that. You really shouldn't be surprised by that. You should not be surprised that when Alice looks at her piece of chalk, she instantly knows that Bob has an eraser.
Even though it's black holes and
No, just entanglement. Just entanglement in general. Entanglement in general happens because in the past systems interacted and became correlated with each other. Correlation is not the same as sending information back and forth. Right. So, and entanglement, which is a deeper idea than just this classical correlation, it's a deeper idea. But at the level of whether you can use it to send information, no, it's the same thing. So, right. So what Alice sees over here may tell her something about what Bob sees over here, but she can't communicate with it.
but she knows something that she wouldn't have known before. If Bob does something and she knows not, whether she can communicate or not, that's information she got. It's not two-way, but
If she knows that the state is entangled in exactly the way in which we as mathematicians know it's entangled, she can ask the question, what field strength will Bob measure over here? And she can answer the question by measuring the field over here. But it doesn't do her any good because she can't get the information from Bob, and she can't get the information to Bob. So there's not been any learning of any, nobody has learned. It's exactly the same as the eraser and the chalk. They are correlated by the fact that earlier on, Charlie did a certain thing, handed one to the other. They didn't know which was which. Once they look at it, they know something about the other one. It is, quantum mechanically, it's more interesting than that, but that's basically what it says. That Alice can know what Bob sees because she's correlated. She's correlated. What's important to the existence of correlation between two things is that they share a common past. That they share a common past, and in the past something happened which, the thing which is happening here is now Charlie is putting the thing behind his back and handing one to the other, and they're getting correlated signals from the past. There's nothing there that violates causality, there's nothing there which sends information faster than the speed of light, but it is a aspect of quantum mechanics which has led to a lot of confusion.
Sounds like information to me. It's not much information, but it's not.
No, it's not the quantity of information. It's the transfer of information. Go back to the chalk and eraser.
So just thinking, yeah, so if we're, so the idea is we're setting up an analogy between, just checking if I got this right, between sort of within the event horizon and the quadrant, the top and bottom quadrants.
Yeah, you would do it,
outside of
this is behind the horizon of Alice. Alice is over here, Milton is behind the horizon of Alice.
Is there any analog of the, so obviously like, very natural to partition the top and bottom quadrants into the top quadrant and the bottom quadrant? Is there any like, I'm not saying what the analogy of that would be for the space-time behind the event horizon. Is there a natural?
Grace.
Well, following up on that question, we're talking about A and B as being the entangled system, but that you're talking about Alice being outside the black hole horizon and Bob being inside, for example.
Well, Bob is not inside. Bob is, this is the inside of the black hole here.
Well, that's the issue. So in the Ringler space, the Milne portion, that's inside of the horizon.
Yeah.
Following up on Matt's question as well.
Yeah.
But then you made the leap talking about how if Alice is outside the black hole and Bob is on the inside.
I used the word Bob on the inside, but that's probably not quite right. This is really where the inside is.
So then we're at 5.
We're only beginning to understand what Bob is. Really, believe me, we're only beginning to understand what Bob is. I will talk about what Bob is next time. And we're going to talk a little bit about wormholes, Einstein-Rosen bridges, and how they are connected with entanglement. Deep connections between entanglement and geometry, and one of the connections is exactly that. I'm purposefully not answering the question now, not because I don't know the answer, but because it's basically the subject of the next lecture. Yeah.
So t goes to infinity as you approach rho equals 0, right?
T goes to infinity as you approach what?
Rho equals 0 as you approach the event horizon. In Wheeler's coordinates.
Omega goes to infinity. Here?
The temperature.
Oh, T temperature,
Yeah,
yeah,
temperature,
yeah.
okay?
Yeah.
So is that similar to the singularity in the Schwarzschild metric? No.
No, it's nothing to do with
Is it
singularity.
real that
The singularity in the Schwarzschild geometry is up here. Singularity is over here.
well, you have fake singularity in the event horizon that
Fake
you can
singularity.
change with a coordinate, with
That's
changing
right.
coordinate.
There's a
right?
coordinate. there's a
Yeah, so I was
coordinate.
asking if this singularity here is real in the sense that I
Which
should
one? Which
expect, well, the one in the temperature. I should expect really an infinite temperature on the event horizon, or is it dependent on the coordinate system?
It's dependent on exactly what experiment you do. So, if you do an experiment where you hold on to your thermometer and don't let your thermometer fall through, that means you subject your thermometer to a huge acceleration as it gets closer and closer, and you send your thermometer along a trajectory which is like that. That trajectory is highly accelerated. That's an invariant statement that the trajectory is accelerated, and an accelerated thermometer will read a temperature. If, on the other hand, you drop your thermometer through, and just let it go, then it will not read a temperature, but you have no way to regain that information. A thermometer which just falls freely through, presumably just behaves like a free thermometer in free space, empty vacuum, sees nothing, but you can't confirm.
What if you fall with the thermometer?
If you fall with the thermometer, you will see the thermometer register 0 degrees, but you won't be able to communicate with Alice. So Alice's quantum mechanics, whatever Alice does, if she can get a record of the temperature, it will say the temperature is high. Let me give you an example. Here's the way to think about it. Supposing we actually drop the thermometer through. Right. You might say, well, then the thermometer doesn't register any temperature. But Alice wants to know what the temperature of that thermometer is just before it falls through. She says, according to my reckoning, the temperature is getting bigger and bigger and bigger as that thermometer is getting near. I want to know what the thermometer registers just before it goes through here. Is it 0 or is it this very high temperature? How is she going to get that information? The only way she's going to get that information is by, you have to look at the thermometer. Looking at the thermometer means hitting it with a photon and having the photon bounce off the thermometer. It's the only way you can look at something, is to bounce something off it. So you bounce a photon off it. You have a photon coming from someplace else over here, bounce off it, and bounce off it, and take the information out about what the temperature of the thermometer is. Well, the answer is, in order to be able to record anything about a thermometer or anything else in a small time interval between the time it passes some point and the time it goes through the horizon, you have to hit it with a photon whose energy is high enough to be able to resolve that small time. Energy-time uncertainty principle. So you have a small time during which you think the temperature is high. In order for Alice to do the experiment, to find out what the temperature is, she has to somehow hit this with a photon, and that photon has to come out. Turns out, and it's very easy to see, that that photon will be enough to heat the thermometer up to the temperature that Alice would have thought the thermometer has to be. So in the process, it's just like any other quantum mechanics experiment. When you try to find something out, you will make an effect on the system, and the effect on the system will be exactly to heat the thermometer up to the temperature that she thought it should have. So whenever she tries to do an experiment on a system on her side of the horizon, it will always be consistent with saying there's a high temperature as you get close to the horizon. On the other hand, if she does no such experiment, and Bob or Mr. Milne falls through with the thermometer, you will see the thermometer register 0. Any attempt to confirm that on Alice's part will wind up heating the thermometer. And that's one of the internal consistencies of the story.
Can I ask a question about the dynamics of what's going on with the black hole and the black hole story? So it doesn't look like it's the case that the black hole gets formed from Alice's point of view. It looks like there was always something weird going on at rho equals 0. And when omega was negative, it was something weird that a lot of stuff was popping out of rho equals 0. And then when omega gets positive, a lot of things are going into it.
We've been talking about a kind of idealized system which is the picture of the black hole at a very late time, long after it was formed. I'm not sure how much to talk about next time. We can talk about a number of things. I don't know how far we'll get. We can talk about the formation of real black holes, how much of these diagrams make sense, which half of them make sense. We can talk about that. We can talk about lots of things, just endless numbers of things. We're not going to talk about all of them. Much of it is sort of standard black hole wisdom. If I had the problem in trying to figure out what to talk about, whether to give a standard course on black hole physics, or to talk about what's been interesting over the last 5-6 years. I chose the latter, and it's at the cost, of course, of being not completely coherent. Because necessarily I will have to jump over things that would be in a course. If you prefer, I will just go through the basics of black hole physics the next time, and we'll just do a standard, absolute standard black hole.
I think we'd like to hear about how space gets up together by.
I think so. I think so. Look, I'm a great believer in learning by osmosis. I think you'll learn things by hearing them a few times. And you will be hearing the story about entanglement in space a great many times in the future. You can learn about black holes by reading any competent textbook on black holes. You can't learn about the things which have happened in the last 5 years that way. So let's, yeah.
Can I just ask one more really elementary question about entropy?
Entropy.
In the beginning of your lecture, you were talking about, this gas in a box that you divide into two halves, A and B.
Yeah.
You assume that the total gas has a unique quantum state.
Let's assume that it has a unique quantum state,
Right.
but a generic one.
Right. And then you have a reduced density matrix for A and a reduced density matrix for B.
Right.
So you assign by your formula a non-zero entropy to A and non-zero entropy to B.
Which will be equal.
Right. Of course, I take it by your information theoretic definition of entropy, the entropy of the combined system A and B is 0.
Absolutely.
Good. But entropy is supposed to be additive.
No. Okay. Coarse-grained entropy is additive. So let me define coarse-grained entropy for you. You divide the system into A and B. You compute the entanglement entropy of A. You compute the entanglement entropy of B, and you add them. It's additive. But let me be a little more precise. What you really do is you take a system and you divide it into small parts. It turns out that a small part can be half the system, but basically you divide it into small parts. And you look at the entropy of each small part, the entanglement entropy of each small part, entangled with the rest of the system. So this piece is entangled with the rest of it. This piece is entangled with the rest of the complement of it, and each piece has an entanglement entropy. And the definition of coarse-grained entropy is just to add them all up. Now, there's a theorem there, and I don't think the theorem has ever really been proved, but it's a sort of folk theorem, and I think everybody thinks it's true, that the answer that you get for the coarse-grained entropy does not depend in detail on how you divide it up.
But so, what you're calling the coarse-grained entropy is the one we run into in thermodynamics.
That's right.
So it sounds like what you're calling the information theoretic entropy doesn't have much to do with what we...
But the coarse-grained entropy of the whole isolated system is the thing we would use in thermodynamics for the whole system.
Right.
But really what we do is we look at small systems embedded in heat baths. So if you want to think about the small system embedded in the heat bath, the entropy of the small system embedded in the heat bath is just the entanglement entropy with the rest of the system in this situation.
I'm not sure where that leaves us. So does the information theoretic entropy, is that the one we run into in thermodynamics, or is it what you're calling the coarse-grained
Yes,
entropy?
under a certain circumstance. The circumstance is that we have a big system that includes a heat bath and the system we're interested in. We focus on some subsystem, we put it in a heat bath, okay? But now we take the system and the heat bath and put them in a pure state, the whole system in a pure state with a given average energy. The theorem is that the density matrix of the subsystem will be a thermal density matrix, and it will be the thermal density matrix that we would use when you're looking at a small system. You rarely do thermodynamics for isolated systems. You do thermodynamics for systems which are in contact with big heat baths.
Well, let's see. I thought the second law of thermodynamics was all about what the entropy of isolated systems can and can't do.
The entropy of an... Yes, it is. It is. It is. The second law is about that, but it's about coarse-grained entropy.
Okay, good.
It's about coarse-grained entropy.
Good.
It's not about the fine-grained entropy. Fine-grained entropy of an isolated system is constant. Is constant, and if the system is in a pure state, it's just zero, as I said. So it's about coarse-grained entropy. So, for example, you can start a system in a product state. Product of this, times this, times this, times this, times this, in a complete product state. Each entanglement entropy is zero. And the coarse-grained entropy, which is by definition just the sum of them, is zero. Then you let the system evolve for a while, it starts to get entangled. I mean, entanglement is, entanglement is not a special thing. Entanglement is, it's like a fishing line. The fishing line tends to get entangled. And entanglement happens, and after a period, massive amounts of entanglement have happened, and now you calculate the entanglement of entropy of this, and this, and this, and this, and add them all up. And you get something large, not small. So that's an example of the increase of coarse-grained entropy. However, the von Neumann entropy, the fine-grained entropy, that has not changed. That help?
Yeah, Boltzmann has a different picture, but yes, I understand what you're saying.
Boltzmann has a different.
Boltzmann has a picture on which what you're calling the fine-grained entropy can change with time.
I would say the fine-grained entropy in classical physics is so infinitely fine-grained that it doesn't mean anything. You always have to define entropy by coarse-graining the phase space a little bit.
No, Boltzmann has a definition of entropy that applies to a single point in phase space.
Okay, I don't
It's
know.
a function of what macro state that point finds itself in.
I guess I don't know that. The only definition of entropy I know is the statistical definition of entropy. I think Boltzmann made a whole bunch of false tries. I don't know where he wound up. But,
Okay, it doesn't, I think there's an equivalent language.
yeah, okay, good. Okay. Next time we'll talk about entanglement in space.